Okay, this is a really important part, the proof of your prediction. So I just took this and I just shrunk it over here. We predicted the larger the mass of the pendulum used to accelerate the bowling ball, the less time it will take the bowling ball to travel a meter. And in the other video, I defined TBB as the time it takes the bowling ball to go a meter, and MP is the mass of the pendulum. Anyway, basically, I just wrote this up here because this will help you get where you're going. This is where we're looking to go. Time is inversely proportional to mass, is basically what you're saying here. So this is how you would start that. First of all, let's look at what you're changing. The mass of the pendulum. Okay, how does that relate to the weight? And I'm just going to do a little subscript P here. We're going to get more into equations for this very soon. Well, as mass goes up, the weight's going to go up. That should make sense because we're on Earth, we're not leaving. So you would just put the alpha sign here. That means directly proportional. As one goes up, the other goes up. Okay. Oh, and I almost forgot right here. Let's be all like fancy and put because. Because, see, I'm explaining right here. Let's see. Now, your weight of your pendulum, how is that going to impact? Remember, this is a butterfly. You catch a butterfly in a net. I didn't catch that one. Okay, so net force, that means the sum total of forces. All the forces, all positive forces added up, all negative forces then subtracted. So the force on the net force of the bowling ball. So how does the weight affect that? And as the weight goes up, there's going to be more force on the bowling ball. There's more to this than what I'm discussing right now, but like I said, and very soon we'll get to that. Now, let's look at this. This is Enduring Understanding 3B. It has this equation and basically says acceleration is equal to, and I'm going to put bowling ball down here. Acceleration of the bowling ball is equal to the net force of the bowling ball, which makes sense. See, like how, see, this one's in the numerator and technically A is in the numerator too. If you have more force, you're going to have more acceleration. That's what that says. All right, so, but this is the equation from 3B over the mass of the, this is important, this is the mass of the bowling ball. We're not going to be changing this, only one bowling ball or car or whatever else. But if you think about this too, if you apply the same force but you have a greater mass, it's not going to accelerate as much. But anyway, this is also just FYI called Newton's second law. More commonly, like you'll hear it like net force is mass times acceleration, but this way is how we're using it now because that's how it was in 3B. Okay, so I'm going to put here, therefore, whoops, and this is kind of obvious, but it's important to state, therefore the acceleration of the bowling ball is, see how this is technically in the numerator and this is in the numerator? That means they're directly proportional. Plus, if you think about it, if you hit something harder, it's going to accelerate more. And yeah, this is just like a sideways M. Net force of the bowling ball. Okay, and we're trying to get to how much time this is going to take. Well, there is another equation for acceleration. Acceleration equals the change in velocity over the change in time. So go up here. Therefore, whoops, and I should put the bowling ball. It's important to subscript things so we know what we're talking about. So the acceleration of the bowling ball, well, let's look and see how that relates to time. It looks like they are inversely proportional. Okay? Now, I'm going to tell you right now, think about the characteristics of velocity. Yeah. Just think about the characteristics of velocity. Think about if there might be more to this. There might be. So anyway, if you catch that, that'll be worth a lot of extra points. But maybe I should have broken velocity down too, because what this is saying is that the time it takes the bowling ball to reach a certain velocity. I don't know. If you don't catch it, that's fine, but think about it. You will definitely catch it when you see your data. Anyway, we'll see who listens. So this is getting pretty close to like what we're looking for, the time. Well, look, you can also say this. See how I just took this from this equation? You don't have to write this next step, but this might be useful. I'm just going to switch this around. If you can say this, if acceleration is inversely proportional to time, you can also write it this way, and this might be more useful. That's supposed to be an A with a vector arrow because acceleration is a vector. So time is inversely proportional to the acceleration of the bowling ball. Well, let's go back. What did that have to do with the force? So therefore, I just put or because you can write it either way. Therefore, the time bowling ball is inversely proportional to the net force on the bowling ball. Therefore, the time bowling ball is inversely proportional to the weight of the pendulum. See how I'm just going back up? Like this one is from the acceleration, this one is from net force, this one, the next step up after net force is weight, and then after that I can get to the time of the bowling ball is inversely proportional to the mass of the pendulum. And that's where I was trying to go. So basically what this is saying is if you have twice the mass, you're going to have half the time. But just remember, and this might affect some of the other ones too, think about this velocity down there, what velocity actually is.